Hey, chemistry people, are we ready for some more? It's, again, going to be pretty quick, pretty short. It says, I can draw qualitative and quantitative connections between the reaction enthalpy and the energies involved in the breaking and formation of chemical bonds. As always, let's take a quick moment to think about that. We discussed briefly in the last video the idea of enthalpy change for a reaction. We're going to look at it now sort of at the level of the individual bonds that are involved and what's going on in terms of breaking those bonds and forming those bonds when we discuss those changes in enthalpy. So we're going to use what's called the average bond dissociation energies to calculate the enthalpy change for a chemical reaction. Pretty straightforward, pretty easy. Again, something we've done in the past, so it shouldn't take you too terribly long so it shouldn't take you too much time to pick up on it. All right, so first, let's just talk bonding really quick, a little quick refresher here. We're talking about covalent bonds in particular. But essentially, as you think about the bond that exists between two atoms, we've got the negative electrons of one atom and the positive nucleus of another atom that sort of create this electrostatic attraction between the two atoms. It's important to note, though, that as you think about those bonds, if the nuclei of the two atoms get too close together, their like charges will end up repelling more strongly than the opposite charges attract. And then we define what's called the bond length between atoms in a covalent bond as the distance between the centers of those atoms when the potential energy of the electrostatic or Coulombic interaction is at a minimum. Now, you've got a thriller of a diagram at your disposal on your notes. And so as you look at sort of what this is telling us, basically what we're looking for is the perfect distance that exists where we're going to minimize the potential energy between the two atoms. So you can be too far apart, too close together, where we're sort of expending more energy than we otherwise would. I mean, you can't really jam those nuclei too close together. It just requires a lot of energy to do that. But at the same time, if they're too far apart, you'll use more energy than if they're sort of like just at the right distance from one another. Now, there's another great animation from PhET that I encourage you to check out. I put it on the website that sort of helps you better visualize what's going on with this idea of the attractive and repulsive forces that exist between atoms as we form bonds. So as we take a look at this animation here, again, we've got our sort of potential energy diagram, and I've got two atoms here. Looks like neon, but as we come together, there's going to be a point at which, again, the electrons in one of the atoms is attracted to the positive nucleus in the other. At the same time, the positive nuclei are going to be repelling one another, and the negative electrons in both the atoms are going to be repelling one another. And so we're trying to get a distance at which the potential energy is minimized. And so as you sort of look at these vectors that exist, as I move these atoms a little bit closer and closer together, you can sort of see there, if I get them too close, my repulsive overlap there, the purple arrows, are going to outweigh the attractive forces that exist between the negative electrons and the positive nuclei of the adjacent atom. And so we're trying to, again, find that happy point where we minimize the potential energy required to exist. Let's be lazy, right? So I encourage you to sort of check this out. You can pick some different atoms and sort of see what's going on with force. See what's going on with some of those different types of atoms, and where they need to be in order to minimize the potential energy between the two. And as you think about chemical bonds in general, covalent bonds, because we're talking about an electrostatic process here, we've got these attractions between differently charged particles, your protons and your electrons. It's governed by what's called Coulomb's law, which is provided there to you in your notes. It's not on your formula chart, but it's an important formula to understand, and it basically just describes the overall force or of attraction that exists between particles by relating their charges, Q1 and Q2, and the square of their distance that's between those charges. So there are some important relationships that we can understand based on that idea of Coulomb's law, where we're going to have double and triple bonds that are stronger than single bonds, since the double and triple bonds contain a larger number of electrons, or Q, our charge is going to be bigger, our numerator is going to be larger, and therefore those types of bonds are stronger. So, as you think about this then, shorter bonds with atoms closer to one another tend to be stronger than longer bonds with atoms that are further apart. Again, so that distance r is smaller. So stronger when you've got those shorter bonds. Now, why is this important? Why are we talking about bonds and bond length, and what does that mean for us? Well, at the molecular level, in terms of energy, if you are breaking those bonds that are existing between atoms, it's an endothermic process. You have to put energy into the bond in order to get it to break. And again, endothermic changes are typically positive. And then keep in mind when you are going to form bonds, and when you make bonds, that's an exothermic process that releases energy. Again, when you're it's less energy to exist sort of as those bonded atoms than it would be to those higher energy individual atoms. And again, keep in mind those exothermic changes are typically negative values. And it's important to know that, because as we're going to work through some of the problems here, that making or breaking a particular bond involves the same magnitude of energy. In other words, whatever energy is required to break a bond is equal to the amount of energy that's released when that bond is formed. And again, the reason why that's important, as you're going to see here, we're going to look at a list or a data table of bond dissociation energies, and they're all going to be positive values. But when you're thinking then about what energy is released, you may have to flip that sign. And it'll make, I think, a lot of sense when we work through a couple of problems, but just keep in mind that making or breaking the bond, we're going to involve the same amount of energy, just the size, the sign is going to be different, indicating is energy being put in to break the bond, or is energy being released when that bond is formed. Okay, so as we think about chemical reactions, all chemical reactions then involve the making and breaking of bonds. Hopefully you can see where we're going here. The energy required to break all of the reactant bonds is the sum of all of the average bond energies in the reactants. And again, when we're talking about breaking bonds, it's an endothermic term. We have to put energy in order to get those bonds to break. However, or conversely, when we are determining the energy released in making all of the product bonds, it's just a sum of all the average bond energies in the products. And again, it's going to be exothermic in nature. The energy change in the reaction then as a whole is the sum of both the breaking and the making process, and can be negative or positive depending on the relative magnitude of the two. And so ultimately we can use a equation to describe for us that enthalpy change, or the overall change in energy that is required when we are making and breaking bonds. And that is provided to you here in your notes. Note that it's not on your formula chart, and that can also be easily confused with some of the other equations that are on your formula chart. So just take some time to commit this one to memory. As you solve these problems, you're going to think about the overall energy of the required to put in and break the bonds, and then subtract from that the overall energy that's released when the bonds are formed. And again, be careful here, because in the other enthalpy equation, it's products minus reactants. And as you'll learn as we work through the problems, because we're talking bond dissociation energies and they're all positive values, it's going to be reactants minus products. But here's a quick example, and again, note they're all positive values, which is why we have reactants minus products in this case.